So, where the allocations of patients to the various treatment groups fair in terms of the weights, in terms of the average weight. Okay, so this is a question that can be posed to, so remember that the anorexia data, we have 3 treatments, those in the control group, those in the family treatment, and those in what? The CBT group. Okay, now if I am doing the divisions, I am assigning patients over here, and over here I assign patients over 80 kg. Okay, here they are all between 50 and 60, and over here maybe less than 50. That will not be fair because these people, they are maybe underweight, right? Which means their cases are severe than those over here. So if this is, let's say, FT, I will just conclude that, well, FT, they are doing very well. But that's not the case because you unequally assign their weight. So that's the sort of problem you will be dealing with. That's a practical problem if I need to allocate them to the various treatments. You say that there is no, biasness in it, which means the averages before should not differ significantly. And that's an analysis of variance problem. So what do we want to do? Well, we want to be able to tell whether so H0 is that the mean of those in the control group is equal to the mean of those in what? The CBT group, and is equal to the mean of those in what? The family treatment. Is everybody okay? Then H1 will be what? At least one of them differs from all. Are we safe? So, okay. So here, at least one of the mu i's, where I will be, let's say, C, CBT, and then FT, differ from the rest. Something like that. Okay. That's what we mean. If we reject this, then it means one of them, at least one of them, differ from the other. It may be all of them may differ. And we will do a second test called a post hoc test. Did you do that? Good. Okay. So if we reject the null hypothesis, we are going to continue to do what? A post hoc test to know which one has the highest mean, which one has the lowest mean. The analysis of variance test is an omnibus test. It just tells you whether there is a difference. It doesn't really go in and check which one is different from the other. So if we want to know which one, so for example, we may want to select the best treatment. In that case, we can only answer that with what? The post hoc test. All right, okay. So we can test this claim. How do we test this claim? Well, to start with, we start from descriptive statistics. Is that okay? So the first thing we do is descriptives, and this is the graph. Okay? So the graph more or less tells us that is that it? Oh no, we are using the anorexia, right? Okay. So I'll construct a box plot Okay, the data is what? Anorexia. Let's do that first. Then we have formula. So our formula is equal to, this is a pre-weight as a function of what? Trait. Is everybody okay with this? Okay, so that's it. And there it is. So it's not surprising that this data does not differ from what? Normality. If you look at the box plot, there are outliers, but the outliers are on both sides. So it doesn't really has an influence. It doesn't, if you can do a histogram of them and you realize that it's not tilted towards any of the tails. They are almost the same. Okay. So the box plot reveals that they rather do not differ significantly from what? Normality. We can move on again and do a formal test, which is the Shapiro. And as I said, in that case, you can just do it, if you like, you can do it for each of the subdivisions, or at this level, just the whole data set. And the p-value is quite large, almost close to 1. So what do? You fail to reject the null hypothesis. All right? Okay, so here, the Shapiro, we are saying that H0 is that data is from a normal distribution, or the data is normally distributed. Okay, so what do? We fail to reject H0. We fail to reject H0 since p-value so and so, okay, is greater than what? Let's say if at 5% significant level we fail to reject it. Is everybody okay with this? Please, is everybody okay with this? Please, I need you to, yes, so we can move on. Please, is everybody okay with the normality test? Yes. Good, okay. So now we can move on. So first of all, it comes from a normal distribution. The next thing we have to do is to do what? We test whether the variances are the same. Is everybody okay? Okay. So next, so let me put it here. This is test of normality, right? And then the next one will be what? Equality of variances. So the B will be test for equality of variances. So with that, I'm saying that we are going to use what we call the Bartlett test. This one. So what does it say? Bartlett test of what? Homogeneity of variances. It's the same. And as I said, you do this, the mathematics of it in what? In your 333. And so forth. So now, all I want you to know is how to interpret it. That's it. Okay. So the Bartlett test, if you do question mark of it, that also has the formula. So you can use the formula. So that's what we are going to use. And the data. That makes it easier for us. So the same thing, just like we did for the this one. So I can just copy what is here and come and paste over here. Are you following? So that we don't. So I just copy the box plot and then I change box plot to what? Bartlett test. So that will give us so there it is. So for this, we are also saying that H0, remember I wrote it. H0 is that sigma 1 squared is equal to what? Sigma 2 squared, so equal. So what is the Bartlett's K squared is this. That's the test statistic. And now you know what the test statistic is. All right. What is the degrees of freedom is 2 because we have 3 groups. And the p-value is this. So from the p-value, if we are rejecting at 5% significance, what will be your decision? Yes. Are you sure? Yes, 5%. What will we do? We will fail to reject. What does that mean? The variances are equal. Is that okay? Or statistically, the variances do not differ from each other. Please, are you following? So you see, we are doing this before we now go and do the analysis of variance. Right? Okay, so that's how you do analysis. You don't just go straight and then you conduct analysis of variance tests. Check whether all the assumptions are satisfied. Right. So here, I can also give a comment and say that since from the results, the p-value, this p-value is greater than what? 0.05, right? Is greater than 0.05, hence we fail to reject H0 and conclude that the variances are not significantly what? Different. Is everybody okay with this? So first of all, what we are doing is that first we test whether we do normality. The data sets come from a normal distribution. Then we test for what? Equality of variances. And that they do not differ. So the next thing we are going to do is now to test whether these are equal. If they are equal, then it means that this one will be normal mu sigma squared. This one to normal mu sigma squared. This one normal mu sigma squared. So we can say that they come from what? The same population. That's really what we mean by analysis of variance. So please make sure you understand this well. And as for this test, even those doing linguistics, they do some of these tests. So you can go for any interview and they can ask you. Huh? Okay. So even though the name is analysis of variance, it is actually, we are testing for averages. Okay? But it derives its name from that assumption, equality of variance. So we actually, before you do that, you must know that the variances are the same. If the means are the same, but the variances are not the same, they don't come from the same distribution. They may come from a family of distribution which is normal, but you can say that they come from this distribution if its parameters are completely known and the parameters are the same. So please take note of some of these things. These are very crucial in statistics. If outside they say, oh, they come from normal distribution, but if you have sat through this department, yes, they come from a normal distribution, but that's a family. Because the mu is real number. So if you haven't said anything if you have not identified the number. And of course, the variance is what? It's a positive number. Right. Okay. All right. So now, with all this, since the Anova assumptions are satisfied, we can now go ahead to conduct this test. Is everybody okay? So we are going one step at a time, right? Yeah. So if you can't write, you don't type fast. I'll send the script to you on Sakai, so you have access to it, okay, together with the video. But try and type, especially with the codes that we will run. Please, is everybody okay with this? Okay, so now how do we do the analysis of variance? Well, we use AOV. There are other ways of doing it. There's an Anova function and so forth. So, yeah, but I like to use AOV. So AOV is what? Fit an analysis of variance model. AOV. It fits an analysis of variance model. Please, is everybody okay? All right. Okay, now, so how do we use this? Well, if you come down here, it will tell you we have also formula and data. That's quite easy because now we know how to use it. You have to provide the data, you have to provide the formula. And we have done that already, right? So I can go up here. Let's all go up there if you have done the Bartlett's test, right? So all we have to do is to just copy either what is inside here, right? The formula is the same thing we are going to do. So I can copy that, just copy, and then when you come here, you need a name, right? So let me call it my Anova. So then I select AOV and then I put in this formula. So what this means is that we are testing whether the average weights, pre-weights between the treatment were the same. Okay. So we do this, and if there's no error, so it means that we can get our results. Now, we get our results by using summary. So you give your model a name, and then you do it. So this summary will now give us our analysis of variance table, which is just like what you did in 223. Okay, so let's run it. There we go. Let me increase this side. So it's like this. And this is your analysis of variance table. So remember that in you have your SS treatment, TR, then SSE, which is your sum of square error. You did this in 223, right? That's why I said here we borrow from all your other courses. So what you have is that you have source and then degrees of freedom, right? What are they? Is it sum of squares? Yes, so your sum of squares. Then you get your what? Mean, squares, and then what? F. And then you can go on and calculate the p-value. Right. Okay. So here you have your SSTR, you have your SSE, right? And then this will give us SST. Over here will be n minus 1, right? And here you have what? The number of k minus 1. Okay, so this plus that will give me this one. So essentially I have what? N minus k, right? Is everybody okay with this? Okay. Then I have my sum of squares. Oh, sorry, this should be the other side, right? Sorry. So these are treatments. So treatment and then what? Error. And then this means is what? Total. So here I have my SSTR, SSE, and then what? SST. So here I can calculate my mean squares, which is SSTR divided by what? K minus 1, SSE divided by what? N minus K. That gives me, this will give me what? MSE. This will give me what? MSTR. Now, what is the, well, we calculate F, which is MSTR divided by what? MSE. Now, what is the principle behind here? Well, are you listening? My dear lady, what were you doing on your phone? Remove that thing from your... Why? What is the problem? What was I talking about? Yes. We are taking our time to go teach you what you need, then you are there on your phone. So this and that, they all estimate sigma squared, right? Okay. Now, if this is true, if they all come from the same distribution, right? You are going to get this and that estimating the same thing, sigma squared. Remember your sigma squared, an estimate for it will be your MSE, right? Okay. So if the H naught is true, then this and that, they estimate the same sigma squared. If they estimate sigma squared, what will be F? I have two estimators. They are all estimating the same thing under H naught. So under H naught, if they estimate the same thing, what will be my F? They all estimate sigma squared. And I'm dividing them. So what will I get? What will I get? 1. Good. Okay. Now, if this is not true, then my MSTR will be equal to sigma squared plus some shift. Okay, and this shift, I'm not going into the mathematics, but the shift is positive. Remember, this is positive, right? Okay. So if H naught is not true, we expect this to be approximately sigma squared, but this to be sigma squared plus some K, or let's say sigma squared. So the numerator will be sigma squared plus some C, where C is greater than 0. Please, is everybody okay with this? So if C is greater than 0 and I'm doing this, what do you expect F to be? It will be greater than 1. Good, yeah. So that's why this test, you only reject for what? Large values. So that's the principle behind it. It's very important that when you learn this, you understand what the test statistics is. And that's why I'm angry with you. Okay? Don't. If I get up, because I want you to understand whatever we are doing, and I expect you to pay attention. Okay. So, F will be greater than 1 or large if this is not true. So you realize that when you conduct this test, if the value of F is so large, then your p-value will also be very small, which means you reject the null hypothesis. So, all right, so let's move on. So look at this F. From the explanation we have done, what do you think will be the so you see that F is very small. It's even less than 1. So you see the p-value. the p-value cannot be less than the 5% we are dealing with. Right? It's quite large. So this one, what will be our decision? We'll fail to reject H0. What is H0? They have what? Equal mean. So how do we now answer? You remember what we were trying to do? Where is it? The question was, it has to be is the allocation, which is the singular one. Okay. But how do we answer this question from what we have done? Was the allocation fair? Yes or no? Yes. Why? Why? Why would you say that the allocation was fair? Because the averages within the groups are not significantly different. Is everybody okay with this? So that's the sort of question analysis of variance seeks to answer. Is everybody okay? Good, okay. Now, the question will be that, can I move on to do a post hoc test to identify which one has, let's say, the highest average, or which one, why? Because they are not significantly different. Okay. So this is how we set questions. So for those who do not pay attention, then it means you go on. So when I used to set this one, then I say, is it necessary to go? Okay, perform. So, or I will not even, then I say go on. So you go on and do the post, but it's null and void. Because you have not rejected the null hypothesis. Is everybody okay with this? Okay, good. Now let's move on. Let's quickly do that of the post weight. Is that okay? So we are not going to go through all the three. I just want the Anova because I want to go through the post hoc test, and then I can move on to, I have two more things to do. So please, any question? Any question? Okay, so what I want you to do is that let's do this same thing for the post weight. The common room one. Okay, so let's copy this and paste. Remember this, we are going to change this to what? Post. That's the only thing, right? But we want this to be different from the other, right? So maybe I can do it underscore P. Well, whatever it is. Okay, so underscore P. Okay, so let me just equality of means. Average weight for post average post weight data. Post weight. Okay, so that's what we want to do. So let's see how that one works. It's post WT. So you see, I did not get a complete. Okay, so now let's look at this. So there's an issue here. Let's see. How are we going to conclude? So you see, before they started the intervention, there were no difference between the averages of the people within each group. Then we gave them intervention, somewhere in the control group, somewhere in the family treatment group and some were in the cognitive behavioral group. After the intervention, their weights, the average weights differ. How are you going to explain this? Oh, first of all, you need to conclude. How do you conclude? Quickly, we don't have time. How do we conclude from this one? So look at the F value and the P value with what I said over here. So you see that when the F value is large, it leads to what? A rejection of the null hypothesis. If you are using the P value, how are you going to? Remember, you can read it. If you want to translate this into your 223, we can do it as well. Which means we need the quantiles of the F distribution. That's the one they give you the 4-figure table to read. Okay. So in R, that will be KOF. Okay, KOF. Then you need the P. So in this case, because I'm using 5%, I'll use 0.95. Then the degrees of freedom 1 is 2. So DF 1 is what? 2. What about the second degrees of freedom? That's what you have over the DF, right? That is what? 69. Okay, so that's enough for me to get my results. So F, and you can read it from your tables. So it means that the F 0.9, 0.05, 269 is what? 3.12 or 3.13. Is that okay? So this is what you'll be reading from tables. So even when in 223, you are going to say that since F, which is, what was our F? 8.65 is greater than this, what do? What do we do? We reject the null hypothesis. And what's the null hypothesis? That the post-weight average weights are the same. So it means they are not the same. They are significantly different. And this is what I'm saying. The Anova test will not tell you which one is different from the other. All we know is that at least one of them will differ from it. So this one, we can now go on and do a post-hoc test to help us. So if I were to ask you a question on this, I'll ask you to choose the best treatment. And what is the best treatment in this case? No? What is the best treatment in relation to this data? What will you use? I mean the criteria. For the anorexia data, yes. What post-weight? How? So what will be the best treatment? What criteria will you use to the what? Please speak up. Pre-weight. I don't understand. They have pre-weight, post-weight. Now, each treatment will have beginning you weigh them. After you weigh them. What we know is that before they were all not different, right? The averages were not different. Now we've put them through the treatment and we realize that they are different. Is that not the case? Okay. Now, how are you going to choose the best treatment? That's what I'm asking you. Yes. Yes, the post-hoc. How? What is the criteria? Yes, there's post-hoc, but what criteria are you going to use? Which one? Hey, F. Oh. You have to come back to basics. What is the data about? What do you measure? Weight. Okay. So, under what circumstance will you say that this is the best treatment from the data? When speak up and let's move on. Yes. When the weights are greater than the age. Okay, you are a bit close. Yes. Then okay. So the basic criteria here is what? Weight. What weight? Different. No. Okay. So do you want the one that will give you lower weight or the one that will give you the weigh more? Which group? Yes. So that's what I'm. So you want those that will weigh heavier, the group that will weigh heavier, because these are people who do not eat, they are eating disorders. And then you want to intervene so that they eat. If they eat, what will happen? They will gain weight. So of course, I'll take the treatment which will lead to what? More weight. Is everybody okay? Yeah. Good. Because I can also ask you a question in which I want the minimum. That's why I'm asking this. Okay. So let's move on. So we'll say that since H0 is rejected and that the average weights are significantly different, we proceed to conduct a post hoc test to determine the best treatment. Please, is everybody okay with this? So you only consider post hoc test when you reject your null hypothesis. That's what I mean. All right. So how do you do a post hoc test? There are several of them. And of course, for if it's Anova, then you can use the 2K test, right? The 2K's HSD. So this compute what? 2K's honest significant differences. Okay. There are others, but we are going to use this. So you select this and then you put in your model. So in this case, my model is what? My Anova P. My Anova P. Okay. This is, are you following? Are you following what we are doing? Good. Okay. Just next week we will know. Okay, so I ran this, and this is what I obtained. And please, I'll need your attention here so that we complete this quickly, and then I can move on to another thing. Okay. Please, are we all here? Have you gotten your results? So you need to get the first one, which is my Anova P. We change the pre-weight to what? Post-weight. And then we got our results. The p-value was very small, so we rejected the null hypothesis. So it means that at the post-weight, the averages between the control, the FT and CBT may be different. Right? One of them. Okay. And now we want to see which one. I have to. Is that how the? So let me see. I can shift this one here so you see exactly. Okay. Please, do you have your results like this? Okay. So now, please, I need to interpret this. So let's go You've done this in 223, but let's see. So here, we are interested in the highest, right? Okay. So the first group, it compares the control, the average of the control group with that of the CBT. So it's like the control average minus CBT. Good. Now we got the difference to be negative. What does that mean? Which one is higher? CBT. Please, is everybody okay? Please, are you with me? So the first one, we got the difference. So what is happening is that we have X bar of control minus X bar of what? CBT. And this is less than 0. So what does that mean? It means this one is greater than what? That one. Please, is everybody okay? Good. Okay. However, we also construct a confidence interval. So we now remember 3 ways of making a decision in a hypothesis test. Either you use the confidence interval, you use the p-value or the test statistic. So we have a confidence interval, and it's from negative, the lower limit is negative 9.3, the upper is 0.12. What is your decision? Should we reject H naught? Are they the same, or we should fail to reject it? So these are things we've done. We don't need to waste time on this. I'm comparing 2 things. 2 averages, right? mu1 is equal to mu2, because this is actually a t-test framework, right? Good. Now, I find a confidence interval, and the confidence interval from negative 9 to 0.12. What should be my decision? You fail to reject, yes. Because the interval encloses what? 0. Which means you cannot rule out equality. So even though control is different from CBT, that difference is not statistically significant. Please, are you with me? Okay. Look at the p-value. The p-value is above what? 0.05. But it is a bit not so far away, right? Unlike the 0.68 we were getting in 0.9, this is just a little above 0.58. That's why the upper limit is a bit closer to 0. That explains it. Okay. So in other words, the conclusion here is that those in the cognitive behavioral treatment group, their average mean is not different from the control. In other words, that treatment is not different from those that were not given anything. Is that okay? Please, is everybody okay with this? Yeah, so if you are buying that, if you are paying money for it, you might as well stop and stay at home. That's what this means. Okay. Now, the next one compares FT and CBT. Now, if you check this, the difference is positive. What does that mean? Quickly. What does that mean? The family treatment, the average weight is greater than what? The cognitive behavioral treatment. Good. Is this significant? Is the difference significant? Yes or no? Hey, my dear friends. Yes or no? Yes. They are significant. Oh. But you just, the top one is not significant, so how can this one be significant? It's from negative 0.5 to 10.13. Is it significant? No. They are not significantly different because 0 is in this interval. Look at the p-value, 0.08. Will you reject the null hypothesis? Will you reject the null hypothesis? You fail to reject, which means they are equal. Is that not the case? Okay. So what have we found out? Control is not different from CBT. Family treatment is not different from CBT. So we are left with what? Remember here we said at least one. But now we know that if this is what is happening. You have control, you have CBT, you have family treatment. This is not different from this, this is not different from this. What we are left with is what? This and that one. Okay. So now let's see that one. So family treatment and control, this is the result. The difference is 9.3. So 9.3, what does that mean? The family treatment average is way higher than what? The control group. Is this statistically significant? Let's look at it. Is it? Yes or no? Yes. Why? Why would you say yes? Because we reject the null hypothesis. The interval excludes 0. Okay. And look at the p-value. Very small. So that's how you do this. Is that okay? All right. Okay. Wait, we don't have much time. Let me quickly do this. You remember the insect spray data? We talked about the data set on insect sprays, the count and the spray type. Let's do analysis of variance for it. I will say that just follow me, okay, so that we don't waste time. Anova, so let me call it AN insect. Okay, so this AOV, the data is insect sprays. This should be count on spray, I think. We look at this data. When you go home, you can do the box plot and so forth. I'm assuming everything is the same. Okay, so summary of AN insects. So let's look at this. Okay. What will be the efficacy of this insect sprays? The same. The average kills. From these results, please, I'll give you the script, but I want us to go through the interpretation, so pay attention. You may stop when you go home. When I give you the script, you can go on. Let's focus on the interpretation, because that's the most important thing now. Now, what will be your conclusion? Are the sprays, the efficacy of the sprays the same? In other words, the average count, are they the same? Why? We reject the null hypothesis because the p-value is very small. Is that okay? So which means now call him for me. Yes. What are you doing there? How many insect sprays do we have from the table? How many insect sprays do we have? 6. Did you say 6? Please, hurry up. We don't have time. What number did you say? How many sprays do we have? 6. Why? Or why do you say there are 6? Yes, who can help us? How many sprays? Why did you say 6? Because the degrees of freedom is 5. So if the degrees of freedom is 5, why do you say 6? Okay, so it's group. Okay, I'm asking this because I can as well give you the table and take those things out. Why? because you know. Okay, all right. Okay, so that's it. So it means that we can go ahead and do a post hoc test, right? Good, okay. So now let's do the post hoc test. So H not rejected, conduct post hoc. So what we are, can you read about that data insert sprays? Read about it. So now we want to look at which spray should we buy. Is that okay? That is what the question in this will be. Which spray should we buy? Well, you have to read the data. What is it about? Read about the data. What is it? If I ask you which spray should you buy, what will you be looking for? You have to read from the data and the help out for the data. And because this is 6, look at all this. If you have to interpret this, it is a bit tricky because there are so many. But this is what I'll do. Well, I want to select, let's say, so let me select the one with the highest number of count. Is that okay? Highest average count. Okay. So I start first with B and A. B is better than A, right? Is that okay? Good, okay. But it is not significant, so I discard it. The ones that are significant are C and A. So between C and A, which one is better? Between C and A, which one is better? A. But A is not different from B. Is that okay? Good. So I move on. I compare D with A. Which one is better? Good. I compare A with E. Which one is better? Okay. So it means that, what about A and F? F is better. Good. And is it significant? It is not. Okay. So it means that I have gone through, I have compared A. A is not different from B, but C, D, and E, I will just take them off from my nesting. Right? Because now I will only consider A, B, and F. Is everybody okay with this? Good, okay. So then I know that A is not different from F, but F is better than A. Right? So I'm left with what? F and E. So I go down there and check F and E. F and E. Which one is better? F. Is it significant? Yes. So it means that I can also rule out E, right? Okay. So for this sprays, I can choose between F and A, but F is the best one. Check your box plot for this. When you go, we did it earlier. You realize that F had higher kills than all of them. Okay, so that's the sort of thing you do. Otherwise, you go one after the other and you won't finish when you don't have time. Okay. Please, any question? And that's the end of our discussion on analysis of variance. Any question on this? So I've recorded it as well. I'll post it there. And there's another recording that I sent you. Please go through it. You will be able to understand this and be able to do the work quite easily. Okay. Now I'll move on to talk about regression. Correlation and regression. So remember that we talked about correlation What is correlation? A measure of in 111. It's linear association between two quantitative variables. And we had the qualitative ones. We don't have time. I'll send you a video on it for you to watch, which is the contingency coefficient, right? Okay. Now, this one, what do you do? So what are the descriptive statistics on this? Is a scatter plot, right? Okay, so the first thing is a scatter plot. If this increases, and then you can tell us what the correlation is. So let's do a plot of cars. So cars is the speed of a car and the braking distance. So we don't have time, so I can just plot this like this. So this is distance and speed. What can you say about the relationship between the braking distance of a car and the speed? Yes. Yes, what can you say? Quickly, please. This one you don't have to. If you are driving at a top speed and somebody is driving at a slower speed, right? Which one would need more distance to brake? Hey, hurry up. The one traveling faster, right? Good, okay. So what kind of correlation will you be talking about? Positive correlation. Is everybody okay with this? Please, are we okay? Good, okay. Now, we can calculate the correlation with what? Core, right? Okay, core. So it needs x and y, but here, x will be cars. What is x? X is what? Speed. Y is what? Y is distance, right? Okay. Then correlation as method. You remember 111. What were the methods did we use to calculate the correlation? The Pearsons, the Spearman, and the Kendall. They are all here, all right? So the method, if we want Pearsons, we write Pearsons. And then we do this. There we go. So 0.8. Is that okay? So how would you interpret this correlation coefficient? So this is 111, but I expect you to know it here. And you write exactly what this is. The correlation is 0.8. How would you classify this? It is what? Strong what? Positive correlation. What does that mean? In relation to the problem we are dealing with, which is the braking distance of a car and the speed at which the car is traveling. As the speed increases, the distance increases. So this one, you may be at the Road Safety Commission, right? And then you go to the throttle station at Circle, and you display this, and you have your, how are you going to explain it to the drivers? That's what we want you to say. In the layman's term, you take a throttle driver and you show the driver this. How are you going to explain this to the driver? Yes. Yes. The more land you can cover. This is braking distance. The braking distance. For the car to come to a complete halt. And this is the speed at which the car is traveling. Quickly. Yes. Speak up so that they can hear you at the back. And we don't have time, so I have to talk about simple linear regression. So let's. A driver moving at a higher speed. How would you interpret it? Yes, the distance. But what will happen? That's how you are moving fast, and then and then what? Yes. Okay, so if you cannot come to a stop like that, what will happen? Oh, it means you haven't been driving. Yes. It will take a longer time. Yes. What else? You need to. You are doing education. This one, they won't listen to you. Oh, the higher you go, no, they won't listen to that. Yes. If you're on a road, you are traveling at a higher speed, and then an object is in front of you. So that's the consequence. You must explain this with that for them to really understand what you are saying. So if, let's say, I'm traveling at 25, I will need around 100, let's say, feet to come to a complete halt. So let's say I'm on the Nima Highway, and then you see a cattle crossing. What will happen? You go and hit the cattle. And then if you are not careful, you lose your life. If it's a human being, and then if you are not careful, they will lynch you. Because, you are over here, you need to travel at the lower speed, but you decide to, they say you are careless, they will beat you. Like that. So you need to, even though it's statistics, you must tell the person you are dealing with the consequences so that they will understand really what you are talking about. So if you travel at a higher speed, you can imagine if you go to 100, you will need so much stuff. So let's say that's why they do road safety. You are traveling on a hill, and then a car is broken down in front of you. That's what happens. And then they can't brake. If you go here, there's an oncoming vehicle. Here too, there's another one. So you either have to go to the bush or hit this or the other one. That's what causes it. So that's the sort of explanation we want you to do. So whenever you have to interpret any statistical thing, look at the data you are dealing with. That's why statisticians do not work on their own, but you work with experts. Okay, but once they give you the preamble, you should be able to interpret your statistics in relation to the preamble you've been given. Is that okay? So in your exam, I'll be looking at that. Not as this increases that, you have not said anything. That is statistics. Okay, let's move on. Okay, did you do the test on the correlation coefficient in 223? Yes, good. Okay, so we do that test as well. Okay, so here we use core.test. Core.test. So this one will give us we perform the test for association or correlation between pairs of samples, right? Now, how do you do this? Well, this one to two ways. You can do this, or you can even do the formula one, right? Okay. But if you want to use the formula, you have to arrange it in such a way that you have all your values, your quantitative values on one side, and then the groupings. Is that okay? So X, then each of them will go, let's say, so this one is the distance and what? And the speed, right? So I need to arrange all the distance values. Then my X is distance and speed together. So I have distance value, maybe 10, and it is distance. 12, and it's distance. Then by the time I get to the last one, I move on to speed. 20, and it's speed. And so then I can use the formula. Okay. Now, so this one, I need to use the X and Y. When you go home, you can try. We don't have time, so let me just go with this. So go and copy all this quickly. So we want to check whether the correlation between the braking distance and the speed is statistically significant. So what is our X and Y? Let's go up here and copy. Please, you can also look at me. As I said, I'll give it to you so we don't waste my time. So I copy this. You remember we've done correlation, we've done test of hypothesis. So you know what two-sided is and so forth. So here I'm testing whether it's static, so both sides, right? So two-sided. So I can leave it like that. Method, Pearson, Kendall, which one do you want to use? Pearson. But we can use any of them as well. Is that okay? So I can delete this. I can delete that one. Okay. If you can't follow, if you can't type, please look at me. Okay, just follow what I'm doing. Exact, I can take it off. Confidence in level. You have to check your test. If I say 10% significant level, you cannot leave it like this. Right? This is 5% significant level. Is that okay? Good. If it's 10%, you have to take it to what? 0.9. Good. So please take note. Continuity on these ones, I can omit them. So I'll conduct this test, and I want you to pay attention to this so that I can explain the statistics. So data, so Pearson's product moment correlation coefficient. The data is car speed and braking distance. You remember what you did in 223. You calculate the t from r square root n minus 2 divided by what? 1 minus r squared, right? All square roots, right? Good. Okay. So that t is what you get over there. So in 223, you read from tables. This will have t n minus 2, right? Good. N minus 2 as the degrees of freedom. You can read that. Okay. What is the p-value? Quite small. So what will I do? I reject the null hypothesis. What is the null hypothesis? That H naught is that what? Rho is equal to 0. No correlation. As against what? H1, rho not equal to 0. Okay, so you see, it says the alternative, the true correlation is not equal to what? 0. So it means we will reject the null hypothesis and the alternative hypothesis stand, which means the correlation between speed and braking distance is statistically significant. Any question on this? Okay. Now you must take note of this, that, okay, we can also consider the confidence interval. It is between 0.68 and 0.88, which means, remember, your correlation is between what? 1 and what? -1, 0. Our interval is here. It doesn't include this 0. So what does that mean? It means that it is what? Significant. If the correlation were between this and that, we will say it's what? Not significant. And so, because you can't rule out 0. And so, okay. And of course, the correlation coefficient is like what we use the chord to get, which is that one. Yes. Yes, it's not different from 0. But if it is significantly different from 0, then it means H1 stands. So we talk about statistical significance. Is that okay? Yes. So that's what I said, that in statistics we may say that 2,000 Ghana cedis, an average value of 2,000 for one group, is not different from 1,000 cedis from the other group. But you can't go to Medina Market, and if somebody says this is 2,000 face, and then you say, well, from my statistics, 1,000 is not different from 2,000, so I just take it like that. They won't agree. So statistical equality is different from mathematical equality. That's what we talk about over here. Okay. Good. I need you to give me 5 minutes to complete this. Other than that, there's a video on it you watch. Okay. So now, if we have this, I can also talk about simple linear regression. Now, remember that we had this, just 5 minutes, okay? this. So it means that under regression, I'll be interested in something. So if I sit behind the steering wheel, I have control over the speed that I want to go. If I want to accelerate more, I press the accelerator down, then the car will move faster. Is that okay? If I want to go slowly, I go slowly. But the braking distance, you may not have control over it. Because one, it will depend on the type of car you are driving. The condition of your tire, the condition of the road. If it has rained, it is different from when it has not rained. Even the road itself, if it is asphalted, if it's a rough road, if it is, and so forth. All right? So that condition, you won't have control over it. So that's what we can use as what? A response variable. That is giving you different results, because if you look over here, you may have 4 cars traveling at 20. One use 50 feet to come to a complete stop. The other use 40. So that's the difference between what? The distance. That's the randomness you do in your regression, which is y is equal to some beta naught plus beta 1 x plus epsilon. So y is our distance. This, we have control over it, and that's what we are calling what? Speed. But the speed, we may have 2 people traveling at the same speed, but their distances are different because of what? This. And this, what do? You put some normal distribution on it to help us generate this. And that's what you did in 223. Now, in R, we will fit this distribution with what we call LM, which is linear model. Okay, so if you do question mark LM, it tells you that it fits what? Linear models, right? Okay. So in this case, what we are doing is that let's talk about our fit LM, and then we come here and copy. As soon as you have formula, that is good to do, to copy and paste. What is our data? Our data is what? Cars. What is the formula? We've done it up here, so we did not use it. Will this one work? It will work. So we have this as a function of what? Speed. Right. Okay. So I run this, and then I do summary. This is just like what we did earlier. Fit M. Okay, so I expand this, and then so there it is. So I want you to pay attention to this so that I can explain. So the formula we use is distance as a function of speed. Distance is our response variable, y. Speed is what? The x, or our independent variable. Now, the residuals. Remember that in your regression, if you were taught about the residuals, will help us estimate sigma squared, which means we give some normality to it. If we give normality to it, it means should be 0. So you check over there. Is the median 0? Is different from that, right? Okay, so if it follows normality, we expect, let's say, the maximum and the minimum to be on the opposite side. The same. Because you want it to follow normality like that. Okay, so what is here, and because 0 is at the middle, what is at the maximum here should be almost the opposite of what? The minimum, but in opposite sides. So this shows us that there is some sort of deviation, right? Because one is 43 and the other is this. But more importantly, what are our estimates? Remember that in your 223, you state this and then you give an estimate for it. Y cap is equal to beta naught cap plus beta 1 cap S. Of course, you have expressions for beta naught and what? Beta 1, right? And sigma S and so, and then y bar minus what? Beta 1 cap, those ones. Right. Okay. So this is what we find here as the intercept. Estimate. So those are the regression coefficients. Speed. This is beta naught. So our regression coefficient or our regression equation from this is that y bar, which is the average speed, is equal to negative 17.58 plus 3.93x. Remember, this is speed, right? And then this is what? This becomes what? Average distance. In other words, breaking distance. Okay. Now, how do you interpret this? From your 223, this will be interpreted as what? The speed of the car, sorry, the braking distance of the car, if the speed is 0, right? So you now have to come into practical terms. How can a car that is not traveling have a braking distance this much? And the braking distance is even negative. Does it make sense? No. So this tells you that not all coefficients are sometimes scientifically it doesn't make sense. In this case, you cannot have a negative distance. So it doesn't make sense in actual sense. Okay? In practice, it's null and void. But it doesn't mean that it is not significant. So you may keep it in there, and I'll talk about it later on. Now, what about this? How do you interpret it? Well, from your 223, if a car is traveling and I increase the speed by, let's say, at the way it is measured, 1 mile per hour, if I'm assuming it's measured in that sense, if you are interpreting it, this is what we want from you. If I increase the speed by 1 mile per hour, then the expected distance will increase by what? 3.93 feet. The expected braking distance will increase by that. If this were negative, we would have said that it will decrease by that one. So it's the same concept you use in 223. Now the next thing is the p-values. The t, you can test whether these values are different from 0. So for example, this is my time over. Yes. Okay, so let me stop, then you continue with this from the video. Okay, so h naught, beta naught is equal to 0 as against beta naught not equal to 0. And of course, the other one will be h naught, beta 1 equal to 0 as against h1, beta 1 not equal to 0. So you do this in 223 as well. This is what is showing over here. So this one, it is significant, so you cannot take out the beta naught. Okay, it's significant. It must be kept in there. And also, this is also significant, right? And so forth. Now, one more thing. If you remember your R squared. Yeah, so the R squared value is here. So, which means that 65% of the variation in the distance, braking distance, is explained by what? It's regression on what? Speed. And of course, the overall lack of fit test, if you did that one too, that's the p-value you find down there. The F test and then the p-value. So that's also significant. So the regression is significant. So which means approximately 35% is not explained by speed. It may be due to the type of car, the type condition, the road condition, and so forth. And you do this by adding these variables, then you extend it to multiple regression, which you do in your STAT228, and so forth. Okay. So I'm left with one more thing, but it's time. So I'll also send you a video of it, a recording of it on YouTube. So which is on chi-square test. Remember in 111, we talk about chi-square test of goodness of it, and then the normal chi-square, which is the contingency table. For the contingency table, it's just chi.test. And you put your contingency table. Yeah, so I'll send you that, and then you can read it. So please check your Sakai. I'll liaise with UGCS and then get you the date and time for your exam. Please, if you miss it, you come the following year. Not for the exam, but through the class. So please, it's also university. That's our final exam. So if you miss it, I can't grade you. Yes. So please, make it a point to be there. All the best. Let me